of this section, and I don't know that we'll actually have much time to talk about it a little bit, but that's actually the how should I put it? The production decline performance. In other words, when the rate from a well or a field starts decreasing, we call that production decline. And the production decline performance, we call that decline analysis or decline curve analysis. So basically it's production decline performance. And that can be of wells, individual wells, or and or the entire field. The topic is not called production decline performance. If you said that in a meeting or something, people would scratch their heads a little bit. It basically has a name that we use, decline curve analysis. DCA. And why curve? Because in the old days they used curves. They didn't have programs that you could best fit with an equation and so forth directly. So it was the decline. That's pretty clear. It's production decline. And in the old days we used this kind of graphical extrapolation of the decline that started, where you create a decline forecast and it's some curve, a straight line or a curved line, and the analysis is basically the study or performance of how decline curves look. And the topic decline curve analysis is not taught here at the university per se, but it's used extensively, exhaustively in a lot of places in the oil industry, particularly domestic, smaller fields, and where you have a lot of different owners of individual wells. So it's a big topic. It's actually a very important topic, but it's not taught here at the university. So we may touch on it briefly towards the end of this section. And it's natural because basically in order to generate the decline curve performance, you need to have done task 1 and task 2. And once you've done those two correctly for your particular reservoir, you can create the production decline performance. Okay? But this decline curve analysis is kind of a it's a general treatment of how that rate will decline with time, for what reasons. It might be exponential decline, it might not be exponential decline. Why not? Okay? So there's a whole technology there that hopefully at least we'll have a 2-hour session to talk about during the remaining time.
Excuse me, sir.
Yes.
DCA method only is used for gas reservoir oil?
No, gas, oil, solution gas. No, it can be used for all types of reservoirs. Okay. And again, just by chance, the father, if you and it was it's not just because the father of DCA is the same guy. Mike Fetkovich. So all of the original classic papers and, over about a 15, 20-year period, in addition to publishing on the gas performance, the gas rate equations, on the material balance of gas reservoirs, he also kind of fathered the modern decline curve analysis field of engineering. So, but he's over 70, so it's, in fact, he just turned 80 about a year ago. Okay. Okay, so let's get started with the first topic, and that's going to be our reservoir gas rate equation. And that's going to be relating the gas rate with bottom hole flowing pressure at the current average reservoir pressure or at the current boundary outer pressure. Okay? And to develop this equation, which is going to, I'll just give you the final form of the equation, and then we'll kind of work our way towards how we got there. This equation looks something like this. You got the permeability and the thickness. That makes sense. The higher the permeability, everybody knows Darcys Law, right? We'll just take a Darcys Law. It says the velocity of flow is not the actual velocity. If you were down there measuring particles pass by in millimeters per second, but it's what we call the Darcy velocity, is permeability over viscosity times the pressure drop along a distance, I'll just say L. So we'd be looking at a piece of rock. We're flowing in, we're flowing out. We measure the pressure here, we measure the pressure here, and the pressure drop from the inflow to the outflow over length L. This is the Darcy equation. And if you want to know the volumetric rate, and that is the velocity. This is the Darcy velocity. It is not a physical velocity. It's what we call the Darcy velocity. So the Darcy velocity. Okay. That velocity times that bulk area. Okay? Times the area. And I'm going to call this as a bulk area. Perpendicular to flow. Okay? So the flow is going horizontally, and if you look along anywhere along the core here, it's kind of a circular thing and perpendicular. So in this case, for this configuration, the area would just be pi times the diameter of the core divided by 2 squared, right? Now, realize that that core could be this big, and it would be a porous media if we had a 10 micron tube going through the middle of it. A single 10 micron tube going through the middle of it, but the core is this big. Do you understand? All of the flow is going through that 10 micron diameter tube. But the area we use, if I'm flowing this way out towards y'all, is through this core, the bulk area is this big. Even though the actual flow is only through, well, this is 10 centimeters? I don't know. Yeah, about 10 centimeters diameter. But the flow is going through 10 micron diameter tube, just one of it. That's a porous media. The whole thing is a porous media because you got the one pore. So if, in that case, the porosity is, well, it's not very big. It's, the porosity is 10, what would be, if this is 10 centimeters and the diameter is 10, what did I say, micrometers? Well, it's 10 to the minus fourth or fifth, whatever. It's a very small porosity. Okay, if I put 10 of those capillaries in there, okay, the porosity would increase a factor of 10, right? But the area to Darcy flow is the same. It's this bulk area. Okay? The velocity, if we're flowing with a certain rate going through here, okay, if I've got 1 capillary or 10 capillaries or 10,000 capillaries, okay, if I'm flowing the same rate through this, it's got the same Darcy velocity. But the actual velocity, is divided by porosity. So if I got one little capillary going through there and I got all this flow going through that one, it's got a huge velocity through that one capillary. But if I've got 1,000 of these capillaries making up the pores and a 10% porosity, okay, the Darcy velocity is the same, but the actual physical velocity is much, much smaller. Got it? Okay. So that's Darcy velocity. So it's not equal to the, whatever you want to call it, pore velocity. If you looked inside a pore and caught a ride with a particle flowing along and measured the distance and time, you wouldn't have that velocity at all. So this is Darcy's law. And this is the permeability we're talking about here. And then we've got the pressure drop between the average pressure, exactly how to write this, minus the PWF. We don't actually use pressure in general. I'll have to correct that a little bit. But it's proportional with the pressure drop between the average pressure in the reservoir and the bottom flowing pressure. And we've got the reservoir temperature down here. It has to do with the fact that this is actually a surface gas rate and we're flowing at reservoir temperature, so the conversion from reservoir conditions to surface has to include the reservoir temperature. And then we've got this well here producing from a formation like that. And we're going to assume that it's a circular drainage area. Okay? Up here we showed you that the actual outer drainage area, it may look like a circle, may not look like a circle, but we're going to assume it's a cylinder. It's a cylinder, a circle approximately. Okay, so we're going to make an assumption that even in this middle well, it's got a drainage area, kind of looks like this. Okay? We're going to assume the drainage areas are like that, and this distance is what we call RE. So this RE squared times pi is equal to the actual drainage area of the well. Okay, it's an equivalent drainage radius. It has the same area. We just make it a simple shape. Okay? So, with this kind of geometry, of which I've only taken out a certain angle, we got 360 degrees, you end up with a term natural log RE, which is this distance here, from the center out to here, RE, to the RW, which is just that distance. Okay. And then you've got a term here, minus 3/4. It's not quite right, but it's getting close. Okay? I'm just going to write it this way to begin with. So basically, the rate is proportional to KH. That's true. Bigger permeability, for a given pressure drop, you get more rate. Bigger thickness, proportional to thickness, more rate for a given pressure drop. The temperature and this term down here, is generally for drainage areas of typical gas wells. This whole term here is somewhere typically between 8 and 10, maybe between 7 and 10 or whatever. But it's a number that doesn't vary. If you got a big drainage area or a little smaller drainage area or a small drainage area, it's still in the range 8, 9, 10, 7 maybe. Yes?
Should we put skin there?
We haven't got to skin yet. Okay? Now there's something missing in this equation. You should immediately jump out and say, Curtis, we just spent months talking about PVT, and in the Darcy equation down here, there's a PVT property, and the only damn PVT property you left out. Something's missing, right? Where's the viscosity? Okay, it is missing, the way I've written the equation now. Now I'm going to do this magic trick, and I'm going to put P here and say that it's not really pressure, but it's what we call pseudo pressure. Okay? It's called pseudo pressure. And pseudo pressure is going to be defined as the integral from 0 to true pressure of P over mu Z. And I realize there's a lot of P's in here, so you want a variable to do the integration on. That is basically P over mu Z dP from 0 to the pressure of interest. So if you want to know the pseudo pressure at the reservoir condition, then you would use reservoir pressure here. If you want to know the pseudo pressure PWF, you just integrate up to that, P mu Z dP. And for reasons just to confuse you, the formal definition has a 2 in front of it. Okay, sorry. Later on I'll explain why it's there. Okay? So let's just take a look at that function this is kind of a, it's kind of a, not really gas mobility, it's kind of a, well, let's just look at it. Okay, so this thing starts out going up a straight line to about 100, 150 bar. Okay. And then it starts turning over a little bit until it gets out to about 250 bar maybe. I'm not sure. $300, just the way I've drawn it, something like that. And then from here on, it just slowly, linearly drops down, like that. Not very much, but it almost looks like a constant, but it's kind of going down. And that's what the function looks like. Every gas in the world looks like this. It might be a little higher, a little shifted to the right or left, but it's going to look like this. And this is effectively density over viscosity. That's what that term is expressing. Density over viscosity. But the point is that for a given gas with, let's say, specific gravity or known composition, this curve is given once and for all, from day 0 to day 50, 60 years later when we finish producing. It's the same curve every time for that reservoir, for that gas. And then this equation, we basically know how to find what is the pseudo pressure of reservoir. Well, we just go in, and if let's say that reservoir pressure is here, and PWF is here, right? Well, let's do this pedagogically. Okay, so we'll turn this guy here into a color orange, and then we'll draw that. So that's going to be going, that area under the curve goes up here like that to right there. It's that area there. And then we're going to lasso this guy, make that purple, and make this purple. And then if we integrate out there, we get that area. And it's the difference between these two, that minus that, that's our driving potential. Okay, this minus this is our driving potential. For Darcy's law. That's what's driving the Darcy flow, times kH. And what is that? That's nothing more than the difference between these two. It's that area there. Okay. That's the driving potential. So it's a simple equation. That's it. Reservoir temperature is okay. Pick a number, 8, 9, okay, no big deal. Pressure drop, we know that from our PVT. This is a pure PVT. We can calculate the pseudo pressure from pressure easily with PVT. And then this is the big thing that varies from your well to your well to your well to your well, to my reservoir to your reservoir. The KH is the biggest thing that really differs. And of course, the average pressure, PWF.
What is TR?
Reservoir temperature. Reservoir temperature.
And could you please explain?
In absolute units. Yeah.
And explain more about what is the driving force.
The driving potential, that's this thing here. I mean, in a given reservoir, you've got your well, you own your well. You can't do anything about KH. You're locked in, you're stuck.
Yeah.
Okay? Reservoir temperature, don't buy a refrigerator. Okay? Stuck. The drainage area, big, small, the number's only going to change from 8 to 10 because it's inside the logarithm. Drill a bigger well, it's going to be that big or that big, and the logarithm doesn't make any difference. So what you can control, there's only one thing you can control, that is right there. That you can control from the surface. You can put a small choke, just barely let it go out. Okay, PWF is approximately equal to PR. You're not making much money. You put a big choke, open it to the atmosphere, you get a low bottom flowing pressure, you get a lot of rate. So you have control over the PWF. PR, you're stuck. Only thing we can control is PWF. So this we control.
But if we decrease the PWF to 0, it means that we can produce all the gas in the reservoir.
Well, no, you're just talking about the rate. Okay, you produce at a very large rate, whatever the rate is, but it still might take you 10 years to empty the reservoir. Okay? Okay, is the concept, and this is first order correct in every gas field in the world. First order correct. I mean, you know, we're going to add a few little things onto this, which can be important, but this is okay. So I'm going to explain a little bit of history lesson. Okay. Before the 1960s, plus, almost all gas reservoirs less than this 150 bar. Okay? There's a field called the Hugoton gas field. It's really a huge area. It's in Oklahoma, Panhandle, Texas, Panhandle, Kansas, and into Texas. So it's just like this huge, the pore volume of the Hugoton field, the pore volume, just the pore volume. It's initially at 100, it's initially at 600 psi, which is, what? Help me. 50 bar, initial pressure. Okay? The initial pore volume is about the same as the Ghawar field in Saudi Arabia, or the North field in Qatar. Monstrous pore volume, but it's only got 600 psi. Okay, 50 bar. Okay, that was being produced from, I don't know, the 30s or 40s. And then most of the gas fields being produced in North America were low pressure because they were right there. You drill down 2,000 feet, you got a big gas field, why drill deeper? Okay, not until the 70s did they start drilling deeper, higher pressure. So before then, everything was low pressure, which means that we were in this regime here where, let me just put a median thing here, where we could say that, well guys, this line here, we just assume it's a straight line, right? We don't need all this complication of integration and da da da. It's just a straight line. Okay? And so when it's a straight line, things get easier. So P over mu z is equal to some slope m times pressure. Goes through 0, 0. It's just very simple. M is just it's a straight line. Okay, and if you introduce that, then you end up with the equation for low pressure, the so-called low pressure gas rate equation. You end up with KH 2 because of the integration, PR squared minus PWF squared over TR. And now we've got a mu z term here and the log RERW minus 3/4. Okay. Well, it ends up that if you look at the, well, let's put it up here. If we plot in pink just 1 over mu z, okay, just forget the pressure part, then it looks something like this. I have to make sure it looks like this. Okay, so what it says is that you can pick it at 1 atmosphere or here, you can pick any value of mu z you like in the low pressure region. It's constant. So what they usually do down here is they just pick this at either initial reservoir pressure, or you could just as well pick it at standard pressure, doesn't matter, and reservoir temperature. So you basically, it's just a constant. Okay? So this whole thing is a constant for your reservoir. Okay. KH is a constant. You've got the 2 because of the integration of a straight line. Pressure squared. Okay. You end up with basically C PR squared minus PWF squared. And that was the equation they were using all the time up into the 60s. And then, I think it was the late 60s, early 70s, it was Al-Hussein, Ramey, and I think Crawford, who generalized with the integral to higher pressure systems. They introduced this this pseudo pressure generalization. And they brought the 2 in here because people had already been using the 2 from before. Okay, so they brought it in for reasons. Okay. I don't remember the date for this. Probably it's in the paper here by Al-Husseini, Ramey, and Crawford, 1966. Okay. Okay. You know, realize that most of that just kept getting, the initial pressure kept getting higher and higher and higher. Okay. They started drilling deep gas wells in Oklahoma in the 70s and continues to today. All around the world, there's very little that is discovered that falls into this category of pressure squared low pressure assumption. So basically you have to use today the gas pseudo pressure method. And when they originally introduced this, the nomenclature in the SPE was M of P. And they changed the M of P into this P pseudo pressure nomenclature about 20 years ago, 10 years ago, I don't remember. So this is now the nomenclature used in the SPE. This is the old SPE. So you'll see some papers using the M, and probably Fetkovich uses it. We go look for his equation somewhere. Yeah, he uses the M. And in fact, he uses 1 over mu BG. That's a little, it can be done, it's the same thing, but it's not standard original. It's like P over mu Z. I'll try to explain that to you. So you've got Fetkovich using integral of 1 over mu G BG dP. And the original Al-Husseini, Ramey, and Crawford use the integral of P over mu Z. Actually, I'm not sure that, I don't think it has the 2 out here, dP. So what is BG? Well, BG is standard like that, so that you can rewrite that as the integral of, so 1 over BG, which is what that's there. You've got P over Z, and then you've got TSC over TR PSC. So you got P over mu Z times TSC PSC TR. So you can see they're the same thing. They're just this constant difference. So it's the same thing.
Excuse me, sir.
Yeah.
Would you please explain again why they use 2 in this equation?
Well, you see, the way I've written the equations now, they're for consistent units. Cubic meters per second, permeability given in meters squared. I mean, it's completely consistent units. We don't use those kind of units. We use cubic meters per day, and we use millidarcy, and we end up with a numerical constant that does all these translation of these units, okay? So when people in the early, in the whatever it was, 40s, 50s, 60s, were using this pressure equation here, There's a bunch of constants having to do with units, having the 2 embedded. I think there's just all sorts of things. So the actual equations that people would use, I'll just give you an example. For field units, which I know best, QG in standard cubic feet per day, K in millidarcy, H in feet, pressure in PSI A, temperature in degrees Rankine. What else is there? Viscosity in centipoise. The equation is 0.703 kH P R squared minus PWF squared. This is the low pressure equation, divided by reservoir temperature in Rankine, mu in centipoise, and this doesn't have any units. Okay, that's the equation I grew up with. Okay, what you'll see is Fetkovich writes the number on the denominator is 1.424 or something. Okay, it doesn't. Okay. So that's the low pressure equation I grew up with. That's in the book that we wrote. If I want to do it in pseudo pressure, it ends up that if you include the 2 in the pseudo pressure definition, I can use that 703 still. KH pseudo pressure reservoir temperature. Now we get rid of the mu z because that's part of the pseudo pressure. See, so these guys in the 60s, they wanted people to use it, and the people remembered the 0.703, or Fetkovich remembered 1.424. He had his number there, and they didn't want him to have to learn a new number. And you could do that if you defined pseudo pressure with the 2 there. Then you could do that, but you needed that. Okay. So that's why that 2 is included there. You guys don't understand all these things because you don't remember slide rules, calculators, the fact that a good engineer had about 10 numbers that he or she knew. 5.615, 12 inches, and you learn these numbers because you don't want to look up in a book your whole life. So you just learn them, and then somebody comes with a new paper and says, "Oh, use this instead of pressure squared," and by the way, you have to learn a new number, and then they just lose interest. Okay, they're getting old too. So this way you could keep using the same number, and that's why they did it that way. Okay? All right, take another break.